Hi, I'm Dr. Michail Stamatakis, and this lecture of the TYC Materials Modeling course is an overview of fundamental principles in statistical mechanics. So far in the course, we have studied small entities, focusing on electrons, atoms, and molecules. So now we're trying to make the connection with the macroscopic world. So here is a little schematic of an ice structure, so solid water, at the atomistic and molecular level. And essentially in statistical mechanics, we are asking the question, how do the laws applicable at this scale shape the macroscopically observable behavior of matter? So for example, if you have an ice cube with a typical size of, let's say, 5 centimeters, then how do the laws that are applicable here shape the behavior at this scale? Right, so we're going from the angstrom to the centimeter scale. Now, this is a very large difference in scales, 8 orders of magnitude. So we're going to see how statistical mechanics has developed methods that allow us to answer this question and bridge these vastly different scales. So in the remainder of the lecture, we're going to, first of all, remind ourselves of some concepts in classical thermodynamics. Then we're going to talk about the statistical mechanics framework. Specifically, we will discuss the concept of microstate, the concept of Hamiltonian, and also methods for averaging in order to get the macroscopic observables of a system. And finally, we're going to talk about statistical mechanical ensembles, specifically the microcanonical, the canonical, and the grand canonical ensemble. So let's start with the Thermodynamics Memorandum, right? The reminder of these basic concepts. Let's consider a thermodynamic system, for instance, water at the triple point. So we have our ice cube in equilibrium with liquid water, in equilibrium also with vapor, all of these inside the box. So this is the temperature and the pressure of water at the triple point. And we are looking into a macroscopic description in terms of the intensive variables, for instance, temperature, pressure, and chemical potential. Some extensive variables, like the number of moles or number of molecules that we have in the box, and the volume of the box, the volume of the system, and also the entropy. And finally, some thermodynamic potentials, which are also extensive variables. So we are going to talk about the internal or thermal energy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. So there are some relations between these thermodynamic variables, like this relation that I'm showing here for du, the differential change in the internal energy of the system. So du is equal to T times ds minus P times dV plus this sum over all the components in the system of mu I times dNi. If you don't remember how this can be derived, there is a nice little mnemonic by Maxwell. So we make this box with these two arrows, and then we just put the thermodynamic potential and the variables like this, thinking the following phrase, this is the mnemonic: good physicists have studied under very able teachers. So this little mnemonic has the information about quite a lot of relations like this. So the first thing we note, let's look at the internal energy, is that the natural variables of the internal energy are the volume and the entropy. And of course, the number of molecules or moles for the component I. So the number of moles are always appearing as natural variables of any thermodynamic potential. These are the difficult ones to remember, right? So V and S. Then if we look into the enthalpy, for example, the natural variables would be S and P. right? So these are the variables that are adjacent to the thermodynamic potential. For the Gibbs free energy, temperature and pressure are the natural variables, etc. Now, in order to write the relation, of course, the differential of u is going to be something times the differential of one natural variable plus something times the differential of the other natural variable, etc. This term always appears. So what are these things here? You see that the variable in which the arrow points is temperature here, and then here the other arrow points to the reverse direction, so we're going to have a minus sign over there, and the conjugate variable of volume is pressure. So we have T times ds minus P, because the arrow is pointing backwards, right, from pressure to volume here, times dV plus the sum of mu I times dni. So we know that the partial derivative of u over s, right, which is basically this term over here, this is simply equal to the temperature. And this is the partial derivative, keeping the volume and the number of moles of the components constant. Similarly here, right, by the rules of partial differentiation, so essentially the partial derivative of u with respect to v, when we keep s and ni's constant, this is simply minus p, whatever we read from here. So these are some other equations that we can derive, again, from this mnemonic by Maxwell. Similar relations hold for the other variables. These relations are summarized here. So let's look at the Gibbs free energy, for example. We said that the natural variables are T and P, and then we see that the arrow points from the natural variable to the conjugate variable. So we're going to have a term which looks like VdP. Here is this term here. Then in this case, the arrow points to the other direction from the conjugate variable to the natural variable. So this is going to be a term S dt appearing in the equation for dg. This is exactly this term here. And of course, we have this term which always appears in all of the equations for the thermodynamic potentials. So you can refresh your memory on all of these and try to derive them based on this thermodynamic mnemonic. Of course, if we now use these equations, we can derive these equations that relate different chemical potentials with respect to each other. So these are the equations here. The enthalpy is the thermal energy plus PV. The Gibbs free energy is equal to the enthalpy minus Ts. And then the Helmholtz free energy is U minus Ts. This is also equal to G minus PV. And this is also equal to H minus PV minus Ts. So I always remember that the enthalpy is kind of like the biggest one of all of them. So it includes the Helmholtz free energy, which is the quote-unquote smallest of all of them, plus PV plus Ts. And then you can remember this kind of this second mnemonic in order to be able to quickly derive these equations here. Now, there is an important theorem, Euler's theorem, which allows us to derive an additional thermodynamic equation. So let's discuss the theorem by Euler first. So this theorem applies to first-order homogeneous functions. Such functions satisfy this equation here. So the function, if the function is homogeneous, then if it's evaluated at lambda x1, lambda x2, etc., lambda xn, then this expression is equal to lambda times the function evaluated at x1, x2, etc., xn. So if this is the case, then f, this function, at x1, x2, etc., is equal to a sum over I is the number of variables that enter this function, so I going from 1 up to n, of the partial derivative of f with respect to xi times xi. And of course note that this partial derivative is taken with all the other variables kept constant. So if this function is homogeneous, then it can be expressed like this with respect to its partial derivatives with respect to each one of these variables. So we can apply this theorem to the internal energy, because the internal energy is a first-order homogeneous function of extensive variables. So U, as we said earlier, all of these thermodynamic potentials are indeed extensive quantities. So U is a function of these natural variables, the volume, the entropy, and the number of moles of each one of the components. So if we imagine if you have a system and then you try to increase the size of that system, let's say you double the size of the system, then of course the volume has to double, the entropy will double, the number of moles of each of the components will also double, and of course the internal thermal energy will also double. So all of these are extensive variables. The Euler theorem applies, so we can express U with respect to its partial derivatives, and this is exactly what I'm doing here. So U is equal to the partial derivative of U with respect to volume times the volume plus the partial with respect to entropy times the entropy plus a sum of the partial derivatives of U with respect to the number of moles for each of the components times the number of moles. And of course I sum over the components. So we know from the discussion that we had in the context of the Maxwell mnemonic, we know that this is simply equal to minus pressure, this is equal to temperature, and of course this is equal to the chemical potential. Therefore, we derive this equation here that tells us that the internal energy of the system is minus PV plus TS plus sum of chemical potentials times number of moles for all of these species. So we just reviewed some fundamental equations from chemical thermodynamics which enable us to study the interrelation of heat and work with chemical reactions and with physical changes of state. So basically, if we have an ice cube, these equations can tell us how many moles are going to convert from the solid phase to the liquid phase when we apply some heat into the system, for example. If we have a reactive system, again, if we perform work in the system and maybe cool it down, etc., then some reactions are going to happen, and these equations that we just saw allow us to predict what is going to happen in terms of the shift in the equilibrium of the system when we apply heat and work, etc. Of course, the question is, how are these macroscopic processes, properties, or quantities related to the molecular world, and specifically the interactions that we see at the atomistic and molecular scales? Right, so this was the question that we posed in the beginning, early on, trying to predict the macroscopic quantities by just knowing what is going on at the microscopic level. Now, particles like atoms or molecules at the microscopic scale obey known laws, like the Schrödinger equation, if we're looking into a quantum description of nature, or Newton's laws of motion, if we're looking into a classical description. And of course, in order to use these laws, we have to know the interparticle interactions, which of course are assumed to be known. So the question is, what are the observable properties of a system that consists of a very large number of such molecules or atoms? So this is the challenge of the problem that we have at hand. we have to deal with a very large number of such particles. So 1 mole of water, right? So 18 grams of water. In order to try to solve these equations of motion, let's say we're looking into the classical description, we would need to solve order 10 to the 23 such equations. So we're talking about septillions of equations, microscopic equations of motion, which are clearly impossible to solve. Obviously, this comes from the Avogadro's constant, remember, so 1 mole of matter has n Avogadro particles, and Avogadro is 6.023 times 10 to the 23rd power. So it's clearly impossible to solve Newton's laws of motion for so many equations, and of course it would be much worse to try to solve the Schrödinger equation for this many particles. But what we can do is invoke statistical arguments. And this is precisely what the statistical mechanics framework allows us to do. By invoking statistical arguments, then we don't have to solve precisely for the position and the momentum of every single atom in our water crystal. We can invoke statistical arguments and make certain statements about the macroscopic properties of our ice cube here without having to precisely solve for all of these variables. So in the next part, we're going to talk about the statistical mechanics framework, focusing on these concepts: microstates, Hamiltonian, and averaging.